Hello, welcome. In this video, we're looking at these three true and false questions, and let's just tackle them one at a time. So the first one says, are all equilateral triangles similar? So I'm just going to do a rough sketch of two equilateral triangles that are different size. By definition, the equilateral triangle has three equal angles in it and three equal sides. How do we know that? Well, if you have two equal sides in a triangle, we can prove that the angles across from them are both the same. So that means that the third angle, right, has to be also the same because the third side is congruent to each of the other two sides. So any pair of these three sides, any way we choose them, the angles across from them will also be congruent. So if I chose this side to look at and this one, then the angles across from those two sides are also congruent. So all of these angles are congruent to each other, right? So all the sides are congruent, and then the angles across from those congruent sides are also congruent. We've got three congruent angles. In this other triangle right here, you have three different lengths. They're all congruent to each other, but that means those three angles are also going to be congruent inside for the same reasons. Furthermore, we know a triangle has 180 degrees, and if you divide it by three equal angles, they're each 60. So there's no way to construct in Euclidean geometry a triangle that has all equal sides and doesn't have all equal angles. So the requirement for similarity that we often use is angle-angle similarity, which tells me that if I have one pair of corresponding angles, maybe they're both in the top of this triangle, that are congruent, and another pair that are congruent, that's enough to say that we have two similar triangles. We could say, of course, also the third pair has to be congruent as well, but we don't need to often say that, because if two of them are congruent by the no-choice theorem, the third pair also has to be congruent. So by angle-angle similarity, this is always a true statement. Okay, what about the second one? It says, so we write true in the first one. And the second one says all right triangles similar. So let me try to think about this. All right, so one case, classic case of a right triangle is a 45, 45, 90, which has 1, 1, radical 2 for the sides. For the Pythagorean theorem, you could figure that out. But then if we construct a 30, 60, 90 as an example, this would be like 60 degrees, this would be 30, this would be 90. If the hypotenuse of that was 1, this length down here is a half, and this is radical 3 over 2. Again, it's an application of the Pythagorean theorem and a small proof about these triangles. Are these triangles similar? No. You can tell from the angles it doesn't have angle-angle similarity, first of all. But also, if we were to, let's say, compare the ratio of one hypotenuse to another, we get 1 to radical 2. But if we do, let's say, a leg, 1/2 to 1, if these triangles were similar, all of the corresponding pairs of sides would have to be proportional. But the ratio of 1/2 to 1 is not equal to 1 to radical 2, so this is false. All right, what about the last one? Are all isosceles right triangles similar? Well, in this case, the answer is actually yes, and let's talk about why that is. If you have an isosceles right triangle, that means two sides are equal, the angles across from them are equal. Let me reason that from the very beginning. So if you have a triangle that has two equal sides and a right angle, those two sides must be the legs, the third side must be the hypotenuse, because the hypotenuse has to be longer. And if these two sides are the same, then the angles across from them are the same. And a triangle is 180 degrees, so 180 minus 2x, where x is each of those angles, has to be 90, the other remaining angle. And if you solve this equation, you would get that x equals 45, which is the value of each angle. So this is a 45, 45, 90. That's what the triangle we're looking at. The one I drew above as well. Now, in this case right here, if I know that I have an isosceles right triangle, I have two congruent sides and thus two congruent angles across from them. So any isosceles, let's draw another one here. If I draw it bigger, right? The hypotenuse if I align it correctly, it will be parallel to the other one. We have this angle here and this one, which are congruent to the other two angles in the initial triangle. And you can see then that, okay, well, in this case, you have two congruent sides. They might be longer, depends what our scale factor is, but we definitely have it by angle similarity. This is actually true. All right, I hope that helped.